Welcome back. This is Tipanis Chachio. You are watching the second lecture in the series Quantum for Beginners. Section 1.2 Classical Mechanics versus Quantum Mechanics. To understand the big picture of quantum mechanics, let us compare it with something that we are already familiar with, the classical mechanics. It is also a good opportunity to refresh our memory on the Newton's second law of motion. However, the purpose of this review is not to refresh all aspects of classical mechanics, which we have studied in introductory physics, but only focus on the parts that will help us compare and contrast with quantum mechanics. Classical mechanics. We are interested in the motion of a particle of mass m, and for the sake of simplicity, confined to move only in one dimension. Specifically, by using the analysis of classical mechanics, we want to know the positions x of a particle at any given time t. Looking back on the problems, exercises, or exams during introductory physics class, we find that a lot of discussions are focused on how to find the position of an object as time evolves. For example, the position of a box sliding on an inclined plane, the position of a football launched into the air in a projectile fashion, or the position of a planet as it evolves around the sun. To compute the function x of t, first we need to know the net force acting on the particle, combined with the Newton's second law of motion, which is one of the main equations of classical mechanics. We can write F net is equal ma. But the acceleration a is the change of velocity with respect to time, or a equals dv by dt. And the velocity itself, by definition, is dx by dt. Therefore, we can rewrite the Newton's second law in the following form. F net is equal to the mass times the second derivative of x with respect to time. It is not too far-fetched to say that the equation is at the heart of classical mechanics, whose applicability includes not only simple exercises or exam problems the students have seen, but also the motion of fluid, the diffusion of chemical agents in solution, or the kinetic of gas, and so on. It is an important step in science that Isaac Newton published in his famous book, mostly known as the Principia. Before moving further in the discussion, let us look at a specific example on how to use this particular equation. Problem 1.1. Verify that in a one-dimensional motion, if the net force is constant, F net is equal to F0, then the position of an object can be written as a function x of t is equal to 1/2 f0 over m t squared plus v0 t plus x0, where v0 and x0 are the initial velocity and initial position respectively. We experience the motion of an object under constant forces every day. An apple falls from a tree because of the gravity, which on the surface of the earth is relatively constant and is equal to mg. An elevator is lifted up because of the tension in the string, which in many instances are approximately constant. Solution. We simply need to substitute the function x of t given in the problem into the Newton's second law in the equation 1.2. And if the function x of t is valid, then it will make the equation holds true. First, focus on the right-hand side of the equation. I will assume that you are vaguely familiar with how to compute derivatives, and will keep this assumption only within the first chapter, giving you enough time to go back and review what you have learned in your calculus class. As an example, d by dx of a huge function with multiple terms inside. The rule is that you can break them into pieces and compute the derivative of each term separately before adding them back again. Focus on each term. The rule is that if there are constants still inside, you can take them outside or factor them out. What is left should be a relatively simple function to handle. For example, d by dx of x raised to the power n. We simply take n down here as a multiplying factor times x raised to the power n minus 1. The derivative of sine x is cosine of x, or d by dx of a constant is 0. In fact, you can look on the internet or calculus textbooks for a whole list of functions and their associated derivatives. Coming back to the problem 1.1. In the first derivative of x with respect to time, we can expand the derivative into the sum of three separate terms. In the first term, since 1/2 f0 over m are constants, we can take them outside. What is left inside is d dt of t squared. For the second term, we have the constant v0 times d dt of t. The last term can be kept just the way it is, keeping in mind that x0 is a constant. As mentioned earlier, for the derivative of t squared, we can simply take the number 2 down here as a multiplying factor, times t raised to the power 2 minus 1. Therefore, the first term becomes 1/2 f0 over m times 2t In the same fashion, d by dt of t is simply a number 1. Hence, the second term is v0 in the last term, because x0 is a constant, meaning it can never change in time. That is why the last term becomes 0. Simplifying the entire expression, for the first derivative, we have f0 over m times t plus v0. But on the right-hand side of the Newton's second law in equation 1.2, we need the second derivative. Therefore, we have to continue to take derivative one more time. Repeating the process using the rules we have just mentioned, such as breaking the expression into pieces or factoring out constants, we find that the second derivative of the function x of t with respect to time is f0 over m. As a result, the right-hand side, which we still have to multiply m to it, becomes simply f0. Now, shifting our attention to the left-hand side of the equation 1.2, it says that the left-hand side should be whatever the net force acting on the object is. Well, the problem states that in this case, the net force is a constant f0. By comparing the left-hand side and the right-hand side together, we clearly see that the equation holds true. Therefore, we conclude that the function x of t describes the motion of an object in one dimension if the net force is constant. In other words, we say that the function x of t is a solution to the equation 1.2. As a homework problem, I would encourage you to apply the same reasoning to the following scenario. Verify that in a simple harmonic motion, such as a mass attached to a spring, if the net force F is equal to minus kx, then one possible solution to the equation 1.2 is x of t is equal to a times cosine of square root k over m times t, where a and k are the amplitude and the spring constant, respectively. Once we know the net force acting on the object, be that a constant force, F net equals to mg due to gravity, or a changing force, F net equals to minus kx in the case of a spring, then we can use the mathematics by the name of differential equation to solve for the solution. Coming back to the Newton's second law of motion in equation 1.2, in order to compare with the main equation of quantum mechanics, to have a better sense of how they are different, we need to rewrite the net force on the left-hand side into a new mathematical form. that is, written in terms of a potential energy, V sub x, which will be elaborated in a moment. Consider a mass m moving under the influence of a spring. We know that the force due to the spring is F equals to minus kx. We also know from the introductory physics class during freshman year in college that the potential energy of a spring, V sub x, is equal to 1/2 kx squared. Here, the variable x is the coordinate indicating the displacement of the mass from the equilibrium. Consider a rock moving under the influence of gravity on the surface of the earth. We know that the magnitude of the force is equal to mg, and the potential energy due to gravity, V of y, is mgy. Here, the variable y is the coordinate indicating how high the rock is from the floor. From these two examples, the spring and the gravity, the students who have taken a class on undergraduate level classical mechanics would be able to guess the point I am getting at. That is, the force F and the potential energy V sub x are not independent from one another, but are intimately linked together with a specific mathematical relation, which can be written as the force F is equal to minus partial derivative of V with respect to x. For example, in the case of a spring, which the student can always remember that V sub x is equal to 1/2 kx squared. Therefore, minus derivative of V with respect to x is equal to the constant minus 1/2 k, leaving inside d dx of x squared, which is equal to 2x. As a result, minus dv dx in this case is equal to minus kx. This result is in agreement with the relation in equation 1.3. Now, let us try to verify this relation for the case of the gravity, which the potential energy V of y is equal to mgy minus the derivative of V with respect to y is equal to the constant minus mg, leaving inside d dy of y, which is equal to 1. As a result, minus dv dy in this case is equal to minus mg. The result is exactly the force acting on the falling object, and the negative sign is simply telling us that the direction of the force is downward if we define the positive y as pointing up. As a homework problem, consider the interaction between two helium atoms. Instead of using force to describe the interaction, we can think of it as a potential energy of the system, as indicated. The potential energy V in this case, known as the Lennard-Jones potential, depends on the separation R between the two atoms, where sigma and epsilon are constants. In this case, draw the graph of the potential energy, compute the force from the information given, and find the separation in which the force is zero. Coming back again to the Newton's second law of motion in equation 1.2, rather than using the net force, we can think of it in terms of potential energy V of x, which can be written as minus dv dx is equal to m times the second derivative of x with respect to time. In essence, the equation 1.4 is the same equation as the Newton's second law of motion. But instead of using the concept of force and acceleration that the students are familiar with, we use the terms potential energy V and the position x. The equation 1.4 is an important equation in classical mechanics if you want to analyze the motion of a particle, as shown in the figure. Think of the process as a computer program. There is an input and there is an output. An input is the information we need to know about what is influencing the motion of the particle, which in this case is the potential energy of the system. This input goes into a processing unit where the students think really hard trying to solve the differential equation. And finally, the output is the function x of t, which describes exactly where the particle is at any given time. Quantum mechanics. Think of it as another computer program with the same input but somewhat different output, and more importantly, very different processing unit. On the surface, quantum mechanics is responding to the same question as that of classical mechanics. We want to know where the particle might be. But the way quantum mechanics answers the question is different in terms of the equation being used and how to interpret the solution of the equation. It begins with the information about what is influencing the motion of the particle, represented by the potential energy V of x. This input goes into the equation called time-independent Schrödinger equation, as shown. The word time-independent means that the differential equation does not involve the variable t, indicating the time. The fact that the equation 1.5 cannot say anything about the time of the system may seem rather unfortunate and limited. The reason is that the equation 1.5 is only the simplified version of the Schrödinger equation, proposed by Erwin Schrödinger, an Austrian physicist who received a Nobel Prize in 1933. 33. When planning a physics lesson, an instructor always faces with a dilemma. On one hand, we can begin with a complete set of equations, precise but complicated mathematical definitions, then followed by the details and the applications at the end. The problem with this pedagogical method is that from the student's perspective, who don't know anything about quantum mechanics to begin with, it is bad enough that they are bombarded with unfamiliar mathematics and strange physics ideas, let alone trying to solve the full version of the Schrödinger equation, which depends on both the position and the time. Not to mention the use of complex number with the real and imaginary part. As a result, most students would simply give up. On the other hand, we can begin with a simpler version of the equation, although somewhat limited, but keep in mind that the student needs some time to get to know the new material in the class. And once we have a better grasp of the basic, we will come back to the issue of time in Chapter 3. Looking carefully at the equation 1.5 of quantum mechanics, we see a few variables that are similar to the equation 1.4 of classical mechanics, such as the variable x indicating position, the mass m of the particle, and the potential energy V of x. But there are a few extra symbols in the quantum mechanics equation, namely h bar, E, and psi of x, which will be elaborated in a moment. The symbol h bar is a physical constant, and we see it everywhere in quantum mechanics. It has the unit of energy times time, which is in joules second. However, the discussion in this class will omit the historical and philosophical aspects of the constant h bar, because the time in the class is somewhat limited, and these aspects are not directly related to the applications of the Schrödinger equation. The symbol E is the energy of the system. It is a piece of information obtained by solving the equation 1.5, and this energy of the system will play an important role in explaining the color of the quantum dots previously mentioned, which will be further discussed in section 1.4. The symbol psi, in the context of quantum mechanics, is given a special name called wave function, which is a function of position x as indicated. It does not really matter if we call the symbol the Poseidon's trident instead of the conventional name wave function. This is not intended to be a funny remark, because after all, this is a serious academic lecture. The point is, as Richard Feynman once said, knowing just the name of a bird in 5 languages, you still don't know anything about the bird itself. You only know about the people, their culture, and what they call the bird. To understand the bird, you have to see its behavior, its migration pattern, and its relation to the ecosystem. In the same way, we are going to learn the meaning of the wave function, its behavior, its evolution in time, and its relation to other quantities in physics. As shown in the figure, those students who have had more than a fair share of struggles in a math class would truly and deeply understand that when there is an equation, there's got to be a solution. You can do it yourself, or ask your friend to do it for you, whatever it takes to find the solution. In fact, many professional scientists use computer software to do it for them. Therefore, from a mathematics perspective, psi of x is simply a solution to the equation. From physics perspective, psi of x in quantum mechanics is similar but not identical to the function x of t in classical mechanics, in the sense that they tell us where the particle might be. But to explore the meaning of psi of x, we need to know the basic of probability, which will be discussed in the next section. And once we are ready, we will come back to the meaning of the wave function. Until next time.